A rock nearly 1 mile wide is about to pass closer to Earth than it has in over 400 years. Not a near miss in the panicked headline sense, not a collision course, but the closest approach this specific object has made since before the year 1600, and scientists are calling it a once in 4 centuries alignment. It is happening on June 27th, 2026. It is happening in days, not decades, and almost nobody outside the astronomy community has registered what is actually about to fly past our planet. By the end of this video, you will understand exactly what this object is, how close 2.6 million kilometers actually is in real terms, why something this size sits in the most dangerous size category NASA tracks, and what would happen if an object like this had been aimed at us instead of missing by millions of kilometers. Stay for the part near the middle because there is a detail about how this asteroid was found that most coverage has completely ignored, and it changes how you should think about every object we have not found yet. You will also see exactly when to look up, because for one single week, this object is bright enough to find with equipment sitting in a closet right now. The asteroid is called 1997NC1, catalog number 152637. It was discovered in July of 1997 by an automated sky survey called NEAT, scanning the darkness from a telescope on a volcano in Hawaii. For 29 years, it has been a line in a database. A set of orbital numbers, nothing more. On June 27th, that changes. The asteroid will cross within 2.6 million kilometers of Earth. That sounds enormous until you put it in context. That is roughly 6.5 times the distance between Earth and the Moon. In planetary terms, on the scale of the solar system, that is a graze. Compare it to the distance between Earth and the Sun, around 150 million kilometers. 2.6 million kilometers is less than 2% of that gap. This object is threading a needle through our cosmic backyard. And here is the number that should actually concern you, not because of this pass, but because of what it represents. This is the closest approach this specific asteroid has made in over 400 years. Orbital records only go back reliably to around the year 1600. Before that, nobody can say with confidence where it was. So when astronomers say closest in 4 centuries, they are not exaggerating for views. They are stating the actual limit of what is calculable. The next time it comes this close again will be the year 2133. More than 100 years from now. This is not a recurring event on a human timescale. This is a once-in-a-lifetime alignment of orbital mechanics, gravity, and timing. Now the size, this is the part that matters most, and it is the part most coverage gets vague about on purpose. Estimates place the asteroid between 710 meters and 1.6 kilometers across. The uncertainty exists because size estimates from telescopes depend on how reflective the surface is, and right now scientists do not know if this rock is a bright, light-colored type or a dark, light-absorbing type. The same brightness in the sky could mean a smaller bright object or a larger dark one. Even at the low end, 710 meters is wider than 7 football fields lined up end to end. At the high end, 1.6 kilometers, this object is comparable in length to the Golden Gate Bridge. Picture standing at one end of that bridge and not being able to see a clear path to the other end because of the curve of the structure. That is the scale of rock currently crossing the inner solar system toward us. This places it inside one of the most closely monitored categories in all of planetary defense. Anything wider than 140 meters that crosses Earth's orbital neighborhood gets classified as a potentially hazardous asteroid. This one clears that threshold by a wide margin no matter which size estimate turns out to be correct. Out of all known near-Earth asteroids ever cataloged, this object sits in the largest few percent by size. Most asteroids discovered and tracked are small, a house-sized or smaller, the kind that would burn up harmlessly or, at worst, flatten a few city blocks. Objects above the half-kilometer mark are a different category entirely, and there are far fewer of them confirmed to exist. Here is what almost no other video on this topic is telling you straight. Objects in the size range of 700 meters to 1.6 kilometers are not common impactors in human history because they are rare in number, but because of what they would actually do if one did hit. An asteroid at the upper end of this size range carries kinetic energy equivalent to hundreds of thousands of nuclear weapons detonating at once. Not one bomb, not 10, hundreds of thousands. An impact from an object this large would not stay local. The blast itself would devastate a region the size of a small country. But the secondary effects are what actually reshape a planet. Dust and debris thrown into the upper atmosphere can block sunlight for months. Global temperatures drop. Crop seasons fail across multiple continents simultaneously. The ocean scenario is worse in some ways than a land strike. A significant fraction of Earth's surface is water, which means an impact this size has a real chance of landing in an ocean rather than on land. An ocean impact at this scale would generate waves capable of devastating coastlines thousands of kilometers from the impact point, far beyond anything in recorded tsunami history. This is not science fiction extrapolation. This is the same general mechanism scientists point to when explaining extinction-level impacts deep in geological history. Objects in this size class are the threshold where a regional disaster becomes a planetary one, and that brings us to the detail buried in paragraph 7 of almost every article covering this flyby. The orbit of 1997NC1 is classified as an Aten-type orbit. That means most of its journey around the Sun happens entirely inside Earth's own orbit. It spends the majority of its time on the sunward side of us, closer to the Sun than we are. And a 10 orbit takes less than 1 Earth year to complete a full circuit around the Sun, which means this asteroid is constantly lapping us, swinging past our position again and again over the decades on a tight inner loop, while we trace our own slower path around the same star. This matters enormously for detection. Objects that spend most of their time near the Sun's glare are some of the hardest asteroids to find with ground-based telescopes, because we are essentially trying to spot something against the brightest light source in the sky. 1997NC, one happens to be one we already caught back in 1997, but its orbital pattern is a preview of the exact blind spot that worries planetary defense scientists most. Large objects hiding in the solar glare that we have not found yet, on orbits we cannot predict because we do not know they exist. Stay with this, because here is where the story shifts from history to right now. This week, scientists at NASA's Jet Propulsion Laboratory are not just watching, they are actively measuring. The Goldstone Solar System radar in California has been tracking this asteroid in the days leading up to the flyby, sending radio waves across millions of kilometers of space and reading the echo that bounces back. Radar astronomer Marina Brozovic, who works on exactly this kind of observation, has explained the method in straightforward terms. Optical telescopes only see reflected sunlight. Radar sends out its own signal and reads what comes back, which means scientists get a direct measurement of distance, rotation, and shape, rather than an estimate based on brightness alone. This single flyby is expected to finally resolve the size question that has lingered for 29 years. Is it the smaller bright object near 710 meters, or the larger dark one closer to 1.6 kilometers? By the time the asteroid is past us, that uncertainty disappears. The radar data does more than settle the size debate. It reveals the asteroid's rotation period, how fast it is spinning as it tumbles through space, and it can expose surface roughness, ridges, craters, even the possibility that this is not one solid rock but two objects orbiting each other, a configuration scientists have found before in other near-Earth asteroids. None of that is visible through an optical telescope. Only the radar echo can show it. A rotation period this precise also tells scientists how the asteroid's surface heats and cools as it spins, which feeds into long-term predictions of how its orbit might drift across future centuries. Every refinement made this week becomes part of a permanent catalog used to calibrate future predictions. If the observed orbit drifts even slightly from the predicted one, that gap gets folded into the model, making every future calculation for this object, and others like it, more accurate. Here's the moment this video has been building toward. Picture the timeline compressed into a single week. On June 24th, the asteroid was still millions of kilometers out, climbing in brightness every single night as ground telescopes in Italy and elsewhere tracked it crossing the stars. By June 26th and 27th, it reaches peak brightness, visible through something as modest as a backyard telescope, for anyone who knows exactly where to look. At 11:16 Universal Time on June 27th, it reaches the closest point, 2.6 million kilometers, 6.5 moon distances, and then it begins moving away exactly as fast as it arrived. The asteroid is not crawling through this pass. It is moving at roughly 9 kilometers per second relative to Earth, fast enough to cross the distance from one major city to a neighboring one in well under a minute. That speed is why the entire closest approach window, the part where it is nearest to us, lasts only a matter of hours before it is already retreating back into deep space. Northern Hemisphere observers get the approach, Southern Hemisphere observers get the departure. The entire planet gets a front row seat to an event that will not repeat at this distance for over 100 years. By the way, here's the detail almost nobody mentions. This same asteroid already passed near Earth once before, back in 2022, and it is scheduled to swing close to Venus again later this year. It is not a one-time visitor. It is a repeat traveler on a fixed gravitational track, and 2026 just happens to be the year that track brings it closer to us than it has been in 400 years. So is there any danger? The direct answer scientists give without hesitation is no. Every model built from decades of tracking data places this object's path safely past Earth, with the next remotely similar approach not happening until the year 2133. There is no scenario in current calculations where this rock intersects our planet. The margin involved is not a coin flip kind of safe. It is a 2.6 million kilometer gap, calculated and recalculated using radar, optical tracking, and decades of orbital data working together. The orbit of this object is now one of the most precisely known of any near-Earth asteroid, specifically because of weeks like this one. But that is exactly why this flyby matters beyond a single night of skywatching. This event is a live test of the entire planetary defense detection system. Every measurement taken this week, the radar data, the brightness curve, the orbital refinement, feeds directly into the models scientists use to evaluate every other large object out there that we have already cataloged, and indirectly helps calibrate how we hunt for the ones we have not found. Here's the open loop closing now. Remember the blind spot we mentioned earlier? Large asteroids hiding near the sun's glare on orbits that are hard to detect. 1997NC1 was lucky. It got caught in 1997, decades before this close pass, giving scientists nearly 3 decades to refine its orbit to extreme precision. Not every object gets that luxury. Some are spotted only days or weeks before a close pass. The 2012 case scientists still reference involved a Carrington-scale solar event that missed Earth by only 9 days of orbital timing. A reminder that the margin between a fascinating flyby and a global emergency can be measured in nothing more than timing and luck. This asteroid is not that emergency. This is the version of the story where the system worked exactly as intended. Early detection, decades of tracking, precise prediction, and a safe, well-understood pass. The uncomfortable truth sitting underneath that good news is simple. We know about this one because it was found in 1997. The real risk in planetary defense is not the asteroids we are tracking. It is the ones in that same size category that have not crossed a telescope's view yet, sitting on orbits we cannot model because we do not know they're there. Survey programs scan the sky every clear night looking for exactly these objects, and every year the catalog grows. But completeness for the larger size classes is not the same as completeness for everything smaller than a kilometer. Gaps remain, particularly for objects approaching from the direction of the sun, the same blind spot this asteroid's own orbit sits inside. June 27th, 2026 is not a warning. It is a demonstration. A nearly mile-wide object will pass within 6.5 moon distances of Earth, visible in backyard telescopes, fully tracked, fully understood, and completely safe. The next object this size might not announce itself 29 years in advance. If this changed how you think about what is actually moving through space near us right now, share it with someone who still thinks asteroid flybys are something that only happens in disaster movies. Subscribe if you want to know about the next close approach before it becomes a headline, because the sky is not as empty as it looks. And the next mile wide, visitor is already out there on a clock somebody has not started watching yet.